Welcome to Coy Ralston High School Physics, and we're sitting here at the 41st North Parallel, just a few miles south of it, and we're going to talk about everything tilts towards the equator. Everything on the Earth's surface tilts towards the equator a little bit. Vertical things usually tilt towards the equator. This is a problem that involves the resolution of vectors. So if you're studying vectors, this is something you'd want to look at. The vectors involved include the acceleration of gravity and centripetal acceleration. And as you look at my vectors in this presentation, they are not all to scale, because if they were, sometimes some would be minuscule compared to others. So they're sized so that you can follow the concept. And the sizes change a little bit. But the math is honest. So we're going to use the Earth's latitude of 41 degrees north here, which is we're just a few miles south of that, to do the calculations. We're going to make some incorrect assumptions that make this a little simpler. We're going to say the Earth's perfectly spherical. We're going to say the surface gravity is absolutely uniform. It's 9.81000 meters per second squared everywhere. That'll just make it a little easier for us. At the Earth's geographic poles, you don't have a centripetal or centrifugal acceleration. You're just going in a circle. And at the equator, if there is a centripetal or centrifugal acceleration, and there is, it's directly above and below you, so you don't notice that. This tilt only occurs off equator and off the poles. It's going to be a maximum somewhere in between. I haven't worked out the angle where it's a maximum. So let's look at the Earth from above the equator, and we see our horizontal parallel here at the 41st. We're going to use a rotating frame of reference instead of the conventional inertial frame of reference that physicists use. The correct way to do this is to talk about centripetal acceleration, which is a real acceleration. But this is more intuitive and easier for lay people to follow and easier to work, really, if we use a centrifugal force. If you're really into this, you can go back and calculate it with centripetal. Okay, as the Earth spins, we're going to experience an acceleration here at the equator that is opposite Earth's gravity, which would reduce Earth's gravity slightly. The Earth is actually not a perfect sphere. As it spins, it's kind of liquid pretty much inside. It's squished down a little bit of poles and expanded a little bit at the equator, and it's because of this right here. The equation for centripetal acceleration is velocity at the equator right there at the surface squared, it should be really speed, divided by radius. And when you work this math out, it comes out to a centripetal acceleration of 0.03374 meters per second squared, but we're going to call that centrifugal out. Now, that acceleration is this way. It's not away from the center of the Earth. And as you get towards the poles, it gets less. So we're going to have to resolve some vectors. My 0.03374 meters per second squared, I've made a bigger red vector here. But as you notice, if we go up in latitude at 41 degrees north, it's less. And it's this side, this adjacent side to this triangle. And this is an angle of 41. So if we work cosine of theta is adjacent over hypotenuse, and we put in our centrifugal acceleration here and work it out, it's a less amount of 0.0254 meters per second squared here. Now, if you're an observer up here at the 41st parallel, you've got gravity pulling you directly towards 9.81 meters per second squared towards the center of the Earth. But that centrifugal acceleration is out that way, and those vectors aren't in a line. So we actually have to resolve this vector into components this way and this way. So if you're the observer, one of those is directly up, and the other one is towards the equator. So that's going to be our hypotenuse, 0.00374. The blue is gravity, 9.81 meters per second squared. So if we take the observer's position, the observer sees that vector broken down this way. 0.03374 meters per second squared is the hypotenuse. Let's make a triangle, we can figure out the x component here, the adjacent side, works out to, when you work cosine in there, to be 0.02546, and the y component of that 41-degree angle, triangle, is 0.02213 meters per second squared. So this is the y that adds to gravity. This is the x that's towards the equator. And when we add them, the x towards the equator is 0.02546 meters per second squared. Adding this positive 0.02213 meters per second squared to the gravity reduces it a little bit to 9.78787 meters per second squared. Now I did all of that so I could get this angle, because that's going to tell us how far we're tilted. So if the accelerations lie along the angle, the displacements will lie along the same angle. So when I put in the x component direction up here and the y component direction down here, I've got a triangle with a very small angle. So 0.02546 divided by 9.78787, and work out the angle for that inverse tangent is 0.149 degrees. So it's a very small angle, hardly noticeable. So if the tilde angle is 0.419 degrees, 149 degrees, this should be a 0.149 degrees, like it is here. I just got to fix it there. How much tilt would that be for 2 meters up? Now 2 meters up would be like this. It'd be a very tall, very tall person's nose maybe. Put in tangent because we had the angle and the adjacent side and we're looking for the opposite. And if you take tangent at 0.149 degrees and you multiply it by 2 meters, you get 0.005 meters or 5 millimeters. So at 2 meters up, everything's tilted 5 millimeters towards the equator. Sounds kind of unbelievable, does it? Well, there are 3 reasons why this would be tricky to detect. One, the amount is very small. So it's not very noticeable at all. 2, the surface of the earth or of a lake is not a tangent to a perfect sphere. The equator geometrically is uphill because the earth is, at most points at this latitude it would be uphill. So depending on where you are, that tangent is out of whack by different amounts. And number 3, all the plumb bobs are doing the same thing. All the levels are doing the same thing. All the spirit levels of bubble in it's doing the same thing. All the observers are doing the same thing. So nobody can tell that that's not exactly up. It's a little bit off. So we all suffer the same deflection. It would be tricky to set up a lab to detect this on the cheap. I've tried to figure out a way to do it. It would require a big space, very controlled conditions, and I'm not sure you could do it with one person that knew what they were doing with a budget. So be one of those things you get put some bored NASA scientists on maybe. But yes, we all tilt towards the equator a little bit, and I'll leave it up to you to come up with a way to design the proof.